Sir, I'm just going for the YouTube live
Yeah,
stream.
yeah. After you finish, you please do it, sir.
Yeah. I think. Yeah, I think sir is there. Yeah, I can see him. One second. Yeah, I have made sir as co-host. Yeah. Sir, Rahul sir, can you hear us, sir?
Yes, yes, sir. Am I audible, sir?
Yeah, we can hear you loud and clear, sir.
Yes, sir. Audible. Yes, sir. Audible.
Okay, okay. Thank you. Thank you.
Welcome, sir.
Thank you, sir. Good afternoon.
Yeah, good afternoon. Good afternoon.
Good afternoon. Am I audible, sir?
Yeah, yes, Dhanush.
Yeah, yeah.
Good afternoon to everyone attending this virtual workshop. It's a great pleasure for me to introduce our speaker for this session, who is going to be shedding light on the topic role of materials in failure of mechanical components and fractography. This is a subject in which we should all be deeply interested as materials play an important role in avoiding failure, and fractography can help us understand the materials much better. Our speaker completed his BE majoring in mechanical engineering from Walchand Institute of Technology, Solapur with distinction. Later on, he completed his MTech in materials engineering from NIT Surathkal as a gold medalist. Finally, completed his PhD from IIT Bombay, one of the premier institutes in our country. Currently, he is an assistant professor, Department of Forge Technology at the National Institute of Foundry and Forge Technology in Ranchi. Amongst being an active member of administrative and academic activities, he is a life member of the Indian Institute of Metals and a peer reviewer for the Journal of Materials Engineering and Performance at Springer. Please welcome Dr. Rahul Ramesh Kulkarni. Welcome, sir.
Audible?
Yes, sir.
Yeah.
Sir,
So
audible.
thank you very much, Mr. Dhanush, for my introduction. So I would like to start my speech by giving a thanks to the VIT Vellore for inviting me for giving a talk on the subject called role of materials in the failure of mechanical component. And I want to have thankfulness, show the gratitude towards the organizing committee, chief patrons, conveners, and co-conveners of VIT Vellore for organizing such a good event. So I will start my talk. I will just share my screen so that, okay. Is it visible to all of you?
Yes, sir. Yes, sir. Yes.
Yes, okay. So good afternoon to all. So the topic that I am going to talk today is the role of materials in the failure of mechanical components and fractography. I was listening last two sessions from Mr. Shiv Kumar and Mr. Shobhashis Ghosh, Mr. Shiv Kumar from DRDO India and Mr. Shobhashis Ghosh from Altair India. So they have given some aspect of the material itself. But this lecture, I will fully concentrating on material aspects in the mechanical component. Since this workshop is targeted for the advancement in design and materials for product development. So material plays a very, very important role in case of product development. So maybe it is a processing of material during product development, or it could be the, you can say, the selection of material in the design of component. Okay, so before actually starting, I would like to give some introduction of my institute. This is a National Institute of Foundry and Forge Technology, where currently I am working as an assistant professor in the Department of Forge Technology. At present, at this this institute has formed the guidelines with the United Nations Education, Scientific and Cultural Organization, UNESCO. It is established in 1966 with the Memorandum of Understanding with the UNDP and Government of India. So presently, we are running few courses, basically MTech in Foundry Forge Technology, and ADC courses for Foundry and Forge, advanced diploma courses for that. And we have the program for PhD also in Foundry and Forge Technology. And there are other two departments like in the Department of Metallurgical and Materials Engineering and Department of Manufacturing Engineering. They have their own courses of MTech and UG level. Okay, so with this, I can start with my overview of the talk I can give you. So I'll start with the cause of failure. Then I can talk about why most of the materials fails in practice, though design of the component is good. So all we know, all of we are, most of we are mechanical engineers, and since the audience is from UG level to PG level to research scholars and industry, I will start with a very fundamental thing first, and then slowly I'll go towards the research part so that everybody will get participated into that. Then I will talk about the understanding of the materials and its behavior under different loading conditions and environmental conditions. Then we'll talk about some of the aspects of the fractography. And the stainless steel 304 LN, 304 LN. Okay, and finally I will conclude with a summary of overview of the talk. So in design of the component, we know material selection is a very, very important in material thing. So what are the causes that is design errors 11 times, unanticipated service condition 8%, then uncontrolled environment condition 6%, inadequate inspection or quality control 5%, and material mix is 2%. So these are the causes of failure in design that we come across, and improper material selection we can see here. So if I use the pointer, yeah. So you can see 38% improper material selection and fabrication imperfection 15%. So if you count both of these is going more than 50%. So we understand the importance of the material in fabrication as well as in the material selection. So though we are saying here faulty heat treatment, uh, service conditions, environmental conditions, all they are related to again for the material aspect. So material plays a very important role to design any component or any product development part. So then the question will come, the why material fails in the practice though design of the component is good. So there are basically 3 to 4 points that I would like to emphasize on. The assumptions while designing the mechanical component. This is one of the factor all mechanical engineers are aware that we are assuming something while starting of the design. Very fundamental thing. Then second problem coming to picture is understanding the materials itself, because most of the materials behave in a different way. So understanding the material, its components, its phases, structures, all these things are very important. And then their properties, especially the material flow behavior during different loading conditions and different environmental conditions. So these are the main factor that I would like to emphasize for the material failure in the component design. So what is the assumptions? We'll go one by one. The assumptions while designing the mechanical component, we assume that the body is homogeneous and isotropic. Homogeneous means all over the material, you can see the component, the material is homogeneous, the same material is there. But is it the case always in the practice? It will happen either it could be a cast component, it could be a forged component, it could be a rolled component. So whichever processing has been done on the material or by the extraction of the material itself, we have seen the body is not always been homogeneous in the practice, though we are assuming that. And second aspect, that is isotropic. Isotropic means there are the directional properties you can see which are all over the directional properties are the same, that we are assuming in case of design, except a few materials like you can see composites, where especially we are looking for different directional properties depending on the orientations of the fibers or something, that kind of thing. Okay, but most of the times we can see material is isotropic in nature. There's one more term that I would like to give you that is called as asymmetry. Asymmetry is nothing but the material behave in a different loading condition, like in tensile behavior as well as its compression behavior. Like in case of magnesium alloy, most of the SCP crystal structure, I'm going to that later on. But this is assumptions that we are making while the design, that there we are little bit facing a problem while designing. But some of the aspects of the design, like a factor of safety, has been taken care of failure, but not all the time. So that is a constant again we are able to find there. Then second aspect of the failure is understanding the materials. So there are a variety of materials. We cannot, now we can see a lot of new materials are coming, lot of invention is going on the materials aspect, depending on the applications, requirement, processing. There are many things are happening in case of materials. Like, but basically we can see there are metals and alloys, polymers, ceramics, composites, and smart materials. So these are the basic classification all engineering at first or second year engineering students can learn this part. Like smart materials, you can see in nickel, titanium, alloys or shape memory alloys you can see. In composites also there are variety of composites, like we have metal matrix composites. Then you can see there are polymer matrix composites, ceramics matrix composites, depending on fiber orientation, there are classification. So you can see there are a variety of materials present. So while designing, while selecting the material, we have to take care of all these component of the material very carefully. Then different phases and their properties. If I am going only for one part as metals and alloys, so you know in basic steel also there are different phases, like you can see austenite, you can see ferrite, cementite, perlite is a combination of ferrite and cementite, you can see. So there are different, you can see the material microstructure has characterization. So different phases and their properties are different. So understanding the material before selecting the material is very important. Then third aspect is understanding the factography. So factography is the area where you can see more as emphasis is going on in practice, especially even in industry, that through my little bit whatever experience I have, industrial experience. So based on that, I can see factography plays a very important role. So wherever any component fail, it is going to be helpful for us to revealing what kind of failure that could be, what condition failure could have been happened, or what kind of loading condition that leads to that kind of failure. So factography is the science of revealing the loading condition and environment that cause the fracture by three-dimensional interpretation of the appearance of a broken component. This is a textbook definition, but if you see, it is going to reveal, it is a science behind which it is going to have loading conditions, environmental conditions in three-dimensional, their appearances. So factography plays a very important role in case of failure. So different loading conditions and environmental conditions shows the different features of fracture surface macroscopically and microscopically. So macroscopically, we can see with your naked eye, or you can see up to the 50x with stereographic microscope. So microscopically, there are variety microscope. You can see either by optical microscope, but most of the times in factography, we are using the scanning electron microscope. There could be a possibility of using the AFM, that is atomic force microscopy. Different characterization techniques are available. We can see about the transmission electron microscope also. Okay, so there are microscopically, you can see variety of things looking at the factograph. Then coming back to the understanding the material behavior during loading condition association with microstructural changes. As we are aware that material is behaving on its own, but it has some relation with the microstructural changes. There is a branch called as a structure property relationship. So how the structure is, accordingly the properties of the materials are going to change in all aspects. Okay, so understanding the material behavior not only in loading way, but understanding the microstructural changes of that also is very important. But not only microstructural and behavior, but the environmental conditions. So there broadly, I classified these two parts in loading conditions and environmental condition. In loading condition, one can say the tensile loading, compression loading, impact loading, fatigue loading, creep loading. So tensile, as all of you are aware that if you are pulling any material apart so that you come into picture the tensile loading. Compression, it's together is called as compression. Impact is a sudden loading condition. Any impact is given, jerk is given. So that is impact loading condition. So fatigue loading condition is a cyclic loading condition. So if there is a variation of the cycle, so you can see the application of fatigue in variety of industries like automobile industry or even aerospace industries. Just we had the session behind that, he showed nice aeroplane. So wings of the aeroplane, so they are going under the fatigue loading conditions. So creep loading condition is also one of the very important loading conditions. So creep is generally is a phenomena of the progressive deformation at constant load or constant state condition. Basically, it is concentrated at, you can see it is emphasized that it has been at high temperature, because creep is generally been showing at high temperature. That's why in definition they have said it has been a high temperature condition for prolonged period of time. See that in creep there are 3 to 4 words that's coming into picture. It's a progressive strain or progressive deformation which is happening under constant load or stress. So parameter of load and stress, parameter of strain need to come into picture, and at high temperature. So temperature is also one more factor, and at prolonged period of time. So time is again factor. So the creep curve gets generated based on that. So these are the loading conditions you can see we have to understand before going into the failure part. Then second part is the environmental condition. Just now I talked about the temperature or corrosive environment. And in practice, it is not, we cannot bifurcate that is a tensile or compression. There could be a mixed condition. The mixed condition can be between tensile, compression, or it could be creep fatigue interaction, or one can say it is like tensile and high temperature compression, high temperature tensile, or in corrosion behavior also all these kinds of things are happening at a time. So there is a mixed condition, then the analysis become very critical and very complicated as we are going into the mixed loading condition. Then basically I am concentrating on compression loading condition as an example because most of the manufacturing process like rolling, folding, extrusion, wire drawing, we know that the material will go under the compression loading. So material get compressed. So understanding the compressive flow behavior of the material is very important. So since I belongs to a forge department, so I'll be bringing the forging part, very fundamental thing. Most of you may be aware of this part. So deformation process in which work is compressed between two dies. So product, you can see there are engine, crankshafts, connecting rods, gears, jet engine, turbine parts, and all these things can be made with the help of forging. And if you see the different forging process, there are two types of forging. You can see impact and press forging. So if you have a sudden load, so here load a factor is very, very important. Impact load or press forging. Okay, hammer is come into the category of impact, and you see press forging, the presses, all presses, hydraulic presses are coming in the category of press forging. And there are two aspects of temperature, like cold or hot forging. Okay, so though this is a categorized into two parts, there is one more part that I just missed here, that is called as warm forging, in between cold and hot. And there plays a material is showing very different property at warm forging as compared to cold and hot forging. And in some of the material, it is to be required to have go for warm forging before going for hot forging or cold forging. And then you can see here are two types. One is called as a open die forging, and this is a closed die forging. In open die forging, you have seen this is carried out between the two flat dies, and dies of very, very simple shape. And in place of closed die forging, you see between the two dies which carry a impression. You can see there is a cavity, and the excess material is coming out. We designated it as a flash. Okay, so to understand, so next aspect before going for failure, so we have to understand the role of material in the component. So for understanding the material, so I categorized previously, as you are aware, now the understanding the material itself, then understanding the behavior of the material itself. Okay, there are two different parts. So first, understanding the material itself. So how are you going to go about the understanding of the material? So example is here taken as AZ80 magnesium alloy. Okay, so I will start with the understanding. So very fundamental thing, right? So magnesium alloys, you can see, which is a crystal structure of SCP, hexagonal close packed crystal structure with atomic diameter. Most of the things you will get it in even in periodic table, and most of the chemistry book also you will find this part. So density is around 1.774. This is very, very important in case of magnesium. Just we have to talk with the automotive industry as well as from aerospace industry. So magnesium plays a very, very important role in this case, since the density is 1.74. One can say other way around, today's buzzword is strength to weight ratio. So weight we are trying to reduce and strength we are trying to improve. So that way one can say this is a very key material. Magnesium is going after the steel, titanium, aluminum, and next is coming in the case of metal is magnesium. There are less denser material than also like composite polymers are there. But in case of metals, one can say that density is around 1.74 and melting point is less 650. But the problem with this alloy is that as compared to other alloys, the deformability of this alloy is very, very less. And that is where the people are facing problem. And a lot of research has been done previously. Okay, and still it's ongoing research based on that variety of magnesium alloy. So this is about only the magnesium. So it is easily alloyed with aluminum, zinc, you can see silver and silver. It can be alloyed very easily, and each component of this alloying element have different properties which has been added to a magnesium. Some of the properties, like you can see aluminum and zinc, both are increasing the strength of the material itself, or flowability of the material itself, or you can see during casting the melting temperature get reduced because of that. So all these things factors come into picture by adding the alloying elements to the magnesium. Okay, now you see this is a nice picture. Previously also you might have seen this picture. So where exactly this kind of alloy has been used? So this is you can see the aeroplane. In this the cockpit instrumental panel as made by the AZ31. So aluminum zinc, I'm going to talk about, that's why I brought it very specifically about aluminum zinc alloy. So here you can see the AZ31. So A stands for aluminum here, and Z stands for zirconia, you can see zinc, and 3 stands for aluminum is for 3% and zinc is for 1%, and B is a modification. It is in pure or it is in some impurities present, that way it has get modified B, C, D that way. Okay, those who are not aware, just I am giving the meaning of this. Then coming back to the here also ZK, zirconium or rare earth metals, you can add that the panels which have been given. So here AZ80 alloy, aluminum, zinc, aluminum is around 8%, zinc is 0 to 0.5%. You can see this is ruler panel which has been made by the AZ80 magnesium alloy. So again, this is a picture. You can see one of previous session you have seen this landing gear. So there also the magnesium alloy has been used very interestingly. So wings and seat component where the magnesium alloy has been used. Then you can see another picture where magnesium alloy made up of cabin furniture in Airbus A330. And you can see here complex core sand casted magnesium alloy and here gearbox assembly. So there are, you can see variety of applications of magnesium alloy. Adding to this, this is not shown, but still there is one more property, you can see biodegradable property. It's also very interesting thing in case of magnesium alloy. Weight is less, so biomedical applications of magnesiums are very, very useful nowadays next to the titanium, because previously titanium was very much popular. Since here it is still it is there, but you can see the addition of that is now magnesium with some constraint. There are still researches going on. There are few problems with the magnesium alloy. We'll discuss this. Then here you can see there are few structures even in automobile also. So front end structure, transfer case, engine cradle. You can see seat back or cushion. So header bow, or you can see steering wheel screws. So all these components of the automobile part is made up of magnesium. Now see the importance of magnesium. So out of that, to understand the failure behavior, I have chosen the material which I have worked on that. So aluminum, zinc, magnesium alloy are popular due to low cost, good casting, and good forging characteristic. So, and the MG17Al12 is the second phase in AZ80 series. So if you see the phase diagram of magnesium alloy, magnesium aluminum alloy. So I will go back to the phase diagram. Very fast. Yeah, here you can see here magnesium aluminum alloy. Okay, so here around 8% of aluminum, you can see there is a alpha plus beta. So beta is Mg17Al12. So through phase diagram we'll come to know what is the second phase. So second phase, you are aware in case of steel also Fe3C or austenite or ferrite, there are different phases are present. So I'm not going into the basic metallurgy of that, but to understand the behavior, you have to understand the material also. That's why I'm trying to bring that. So Mg17Al12 is a second phase in AZ80 series with higher hardness than alpha magnesium matrix. Very, very important. So the you can see the proportion of Mg17Al12 decides the strength of the material. Decides the strength of the material. And not only strength of the material at room temperature, but if you are going to process this material at high temperature or you're going to use this material at high temperature, still its hardness remains up to 450 degrees centigrade. That's what I have seen. So 450 degrees centigrade, Mg17Al12 maintain its hardness higher than alpha magnesium. So that will be helpful for processing, since this will constrain the grain boundaries and everything at high temperatures. So final grain structure may be produced and it will go for super precision and all this kind of thing. So going not to details of that, but you can understand here that Mg17Al12 is the second phase in AZ80 series with higher hardness than alpha magnesium. So chemical composition of alloy, that is what I have worked on that. So you can see here, aluminum 7.7, zinc 0.4%, manganese 0.15, silicon 0.2, and balance is magnesium. So aluminum is major component here and zinc is another. Then next to that, manganese and silicon its own characteristic. Okay, adding to that. So once you understand the material, you need to understand the material flow behavior during loading condition. And here we are going to see basically a compressive loading condition. Since we had talked that in most of the forging components, the behavior forces which is going to be act is the compression test. So we are going to see the behavior during the loading condition association with microstructural changes and different environmental condition. Here environmental condition not has been taken as a corrosive because magnesium has one more problem like deformity is a constraint, and another problem with this around the corrosion aspect. So that is studied by the corrosion engineers, but deformation is basically the problem at this point which has been focused on that in this talk. You can see and environmental condition here, time and temperatures. Okay, so the case one is flow behavior during compression test. So you can see we received the material in a as-cast structure, which is a sand caster structure, and this is a microstructure. You can see very beautiful microstructure. In that there are 2 to 3 components. Okay, so one component you can see, this is alpha magnesium. This is the matrix. So major component is alpha magnesium. It's a magnesium alloy. So alpha magnesium, as all of you know, in a metallurgical, basic metallurgical point of view, it's a solid solution of aluminum in magnesium. Since the major alloying element is aluminum and next to that is zinc. So there could be a alpha magnesium addition of aluminum in magnesium. So this is a solid solution. But second phase which just get dissociated out of coming out of that is a Mg17Al12. And due to the cooling rate during casting, you know the casting process, there is a melting and then molding, you are pouring the metal into that and the material is going to shrink and it is get solidified with different solidification characteristics. And during solidification, there are a lot of things are happening. I'm not going into detail of that, but since I'm showing the three components, I'm going to just give you the insight of that, gist of that. During the casting process, you can see that there are different cooling is going to happen, and because of this different cooling rate, like you know it at mold phases you have higher cooling rate. If you go to interior, there is a cooling rate become very slow, and because of this morphologies get created in the microstructure. So one of the you can see the morphology, this is called as fully diversitectic. Fully diversitectic is what you can see. This is a white metal here around in the microstructure. So this is white is the thing, but a second phase alpha Mg17. How I come to know this? So for that purpose, I took the help of characterization technique called as scanning electron microscopy. And in this, what we have seen that if I put point number 1 and point number 2 with the EDS attachment, we found that the magnesium and aluminum percentage is 60 and 37.57. And in case of 2, means in the matrix, you can see 93.49 and 6.03%. Means here aluminum content is very high. So if you try to calculate the ratio with 16.39 as to 37.57, you will find it is a 17 as to 12. That is Mg17, 17 atoms of magnesium and 12 atoms of aluminum. By this method, you confirms that this white portion in the microstructure is the Mg17Al12. Okay, but there are different morphologies I just discussed. So it is a fully diverse eutectic of alpha magnesium and alpha Mg17. So fully diverse indicates that this is Mg17Al12 particle. Around that you can see the alpha magnesium, and again you can have Mg17Al12. Again you can have alpha magnesium. So this is called as fully diverse. It is diverse completely. You can able to see the gamma Mg17Al12 and alpha magnesium. There's another morphology you can see in the microstructure. This is called as partially diverse eutectic. So partially diverse eutectic means it is a partially alpha magnesium and gamma Mg17. How you can see this characterized in the characterization? So you can see this is the magnesium, alpha magnesium in the islands of Mg17. So you can see this is a river, like if you imagine that kind of thing, and in that you see the small gray color portion. This is your alpha magnesium. So you will have the river, or you can see the matrix of Mg17Al12. Into that partially you will have the alpha magnesium, and around that again you can have alpha magnesium. So this is they call it as islands of alpha magnesium into the gamma Mg17. You can see gamma Mg17Al12. Okay, so these are the things you are able to see, and discontinuous precipitation of the microstructure alpha magnesium and alpha Mg17Al12. Okay, so these are the things you are able to see in the microstructure point of view, and basically this is lamellar structure you are able to see, which is, but these morphologies has created due to the differential cooling rate. At this point, I can say that much. If you have few explanation on that, there is one paper which has got published, how this morphology is formed. It is available with me. So if anybody is interested, definitely I can tell you later on. But our focus is basically on failure. Okay, so you can see the compression test has been conducted on this material. So at different strain rates and temperature. When I was talking about the forging, I have mentioned here impact and press forging. Means there are the different rate by which you are able to deform the material. So strain rate plays a very important role in case of the forging of the material. So to understand the flow behavior, you have done the compression test at different temperatures, and we have done the at different strain rates. So you can see there is a phenomena called as recrystallization phenomena is happening. That is called as dynamic recrystallization phenomena, which is happening about 250 degrees centigrade. You can see as the strain increases, the two strain is also increasing, but after particular strain it is coming down, and you can see that the plateau gets achieved. So that is called a steady state condition. So this steady state condition is achieved after certain strain. Okay, so this is termed as a dynamic recrystallization in metallurgical word. You can see physical metallurgy word. So dynamic recrystallization happening because of many phenomena is happening in that. The dislocation phenomena is happening. You can see solute atoms, the diffusion phenomena is happening, going from one place to other place. But very interesting thing you can see here, at below 250 degrees centigrade, material is going to fail by showing very low strain. Okay, so you can see as the strain rate I am decreasing, it is showing a little bit more. You can see the strain, and it is failing because strain rate is low. As the strain rate increases, you can see the strain in the material component is very less. At room temperature, you can see around 30 degree also, maybe term as a room temperature or ambient temperature. Okay, so here material get failed at very low temperature. Okay, so these are the microstructural features after deformation at different temperatures and different strain rates. Okay, so here you can see A, B, C, D, E, F. So A, B, C, you can see these are the three microstructures which has been of the specimens which is get compressed at the 10 to the power minus 2 per second at 250, 350 and 439 degrees centigrade respectively. And similarly DEF at 10 to the power minus 4. As you are decreasing the temperature, you can find that there are small particles which is being associated with the grain boundary. So all this you can find out. This is a grain, one grain, this is another one nicely grain, and this is grain. So around that these small particles are going to be there. So this is Mg17L12. So as the temperature, as you can see, strain rate decreases, the particle is breaking into the pieces. It has sufficient time. Strain rate is low means it's sufficient time at that temperature to breaking into the pieces, or it is get dissolved. In other way, I can say that precipitate get dissolved very easily, and at the expenses of smaller grain, you can see the bigger grain grows, as the metallurgy says. Okay, so that way one can have, and not only that, this precipitates plays a very important role in dynamic recrystallization, act as a heterogeneous site. There is a term as particle stimulated nucleation. So because of that, the final grain structure may appear at lower strain rate. Okay, so this is the specimen. You can see this is breaking into two pieces. So magnesium has a problem. So at room temperature, if you try to deform the material breaking into the pieces. So we tried that at 250 degrees centigrade, the compressed material shows like this, seen like this. At 439, 453, it is look like this. So at you can see room temperature or up to 150 degrees centigrade, material got broken up into two pieces after deformation, and the fractograph try to analyze on that component. So here you can see this is a completely cleavage fracture in both the cases. At room temperature 10 to the power minus 2 per second, and strain rate of 10 to the power minus 2 per second at 150 degrees centigrade. Okay, so and there are a few cracks which has appeared. One can see there are cracks, and this is a cleavage fracture. Cleavage fracture is a completely brittle fracture. It is a completely brittle fracture. No significance you can see here regarding any you can see any characterization that you are able to see in fractograph of ductile features. So this is a completely 100% cleavage. One can say 100% brittle. So then again we are trying to analyze. So actually where this crack has generated. Though material has failed, that's fine, but we have to understand why this crack has generated. Then try to do the again EDS, okay, scan. Then we find, so wherever crack is there, around that you will find the aluminum content is very high. So the reason for failure at low temperature of the material is not only low deformity, but there is a matrix and there is the another you can see phase. So there is an interface between these two. So these two interfaces act as a stress concentration. So stress concentration at there, and because of that material is going to be failed. Okay, so stress concentration lead to the high concentration of stresses, which leads to a crack, and once crack has formed, within no time it may grow and the material is failure. So failure is in different, I'll come to that. Okay, so material is going to breaking into two pieces. The second aspect of tensile behavior, so we have just talked about the compressive behavior, then we are talking about the tensile behavior as a function of time and temperature. You see there is a phase diagram and there is a EDS has been done. So as per the phase diagram where actually alpha beta is converted into alpha, so we find that at 437 degrees centigrade this is going to form, and the two temperatures has been chosen for solutionizing heat treatment. You know, as the solutionizing heat treatment making the material soft for deformation. So this is not only associated with the temperature, but this is also associated with the time for which you are keeping the material into the furnace. So these two factors very important. So we find at 6 hours, 1 hour, 24 hours. These are the tensile tests which has been conducted of the specimens which has been kept at 400 degrees centigrade and 439 degrees centigrade at 1 hour, 24 hours, and 6 hours. And then after filling this component, we try to analyze. So what is happening in case of fractographs? So we find at you can see at 400 degrees centigrade. So 400 degrees centigrade has been at A and D. You can see at A and D for 1 hour there is a cleavage fracture, but at D you can see this is called as quasi cleavage. So this is a term, or you can see this is. So these dimples get elongated in case of D. You can see that very carefully in SCM micrograph. So this dimple is characterized by the ductile fracture. So at lower temperatures, 400 degrees centigrade, there are small dimples are present, no doubt. But most of the times you can see there's a river pattern. River is going like that. And here you can see this is called as a river pattern where it is get material as broken. Okay. So, but here also same thing, but ductility is little bit increasing. But in between 1 hour to 24, there is 1 more hour that we have taken as 6 hours. Lot of crack and tearing edges has found. Okay, and then at higher time, you can see a lot of dimples. But as the temperature increases, the number of dimples has increased. No doubt, the size of the dimples also get increased as compared to this one. It is clearly seen in this. This mechanism is happening. It could happen that the small voids get created at the end of the once the UTS is reached. Here you can see the once UTS gets reached, the small the cavities has formed, dimples has formed, and they are try to gather together, and they will form a crack, and the material will fail. So you can see there are different mechanisms. So why nice structure that I got. I thought I can share this to you. So inclusions in the ductile matrix, void nucleation, void growth, strain localization. So I'll come to that, necking between the voids and void coalescence and fracture. So these voids, all voids come together at the end of the UTS, and they the material is making into 2 pieces. So these are the few mechanisms of the ductile here. Then here whatever has been taken care of, strain localization between the voids. So this is we try to analyze further. One of the specimen we took at 0.3, again we try to analyze what is happening around that through the characterization techniques. So there we find again the aluminum has increased its content, magnesium. Means what? Definitely at the interfaces there is something called as strain localization is happening. And in metallurgical world you can see strain localization happening because of the moment of dislocation, and dislocations are going to be the part of strain localization which will lead to the cracking. But since I have not used the word dislocation, since we have not done any TM based on that to support this part. Okay, but general theory of the metallurgy says like that. The second aspect that try to bring out for the failure, that low temperature embrittlement studies on the stainless steel 304 Ln TIG bed. So you see austenitic stainless steel very widely used in energy systems, nuclear energy systems, good weldability, prime fabrication method for components made up of stainless steel and fusion welding. Basically, this material has been used in the BRC, Baba Atomic Research Center. So found to be a component failed by cracking either during the welding in service through the strength of the weld joint is adequate by design. Though weld joint, again here I can see that weld joint is good, everything has been done correctly, but still material is failing. What could be the reason? So there is called as delta ferrite present in the 304 LNCC, which is having greater solubility than austenite. So you know delta ferrite has a BCC crystal structure. Thermal expansion is very, very low in case of delta ferrite, and because of that it reduces the shrinking stresses, resulting in the improvement of hot cracking resistance. Further, it increases the strength and resistance to stress corrosion cracking. This is a very important key. One can see here the delta ferrite plays a very, very important. It has good advantages, but there is a limitation. So if the pipes which has been used of 304 Ln, which has been at high temperature ranges, the slowly they'll get degraded over the period of time. The people are trying to see that what is happening. So for some of them have predicted that converting into the G phase, M23C6 phase. Okay, so I'm not going into detail of that. It is called as spiral decomposition is happening. Okay, but you can see these are the phases which has formed over the period of temperature and time, and which is leads to the embrittlement. And these are the very, very hard phases which will lead to the embrittlement. You can see this is a welded joint of the pipe, and this specimen for the impact test has been taken from the welded joint in this direction, and the delta ferrite measurement has been done. You can see over edge at 350 degrees centigrade and 400, there is a little bit reduction in the delta ferrite. So where this delta ferrite will go? because conservation of mass or conservation of law says something is reducing, means something should be get converted. So 7, but so this is going into the other phase, which is the embittered phase. Okay, so for that purpose, we have used the Charpy impact test. Okay, so sudden now here coming up the factography of the impact test. So impact test is conducted basically for sudden loading conditions. So you may ask the question why this is happening in pipes. So there could be a possibility in pipes that sudden thermal expansion and contraction leads to a you can see impact loading, vibration due to the occasional loading, sudden pressure variations within the pipe system, motion waves due to flow induced impact. So there are many reasons by which the impact load is going to happen in the pipe also. Okay, so the test was conducted at different temperatures from -70 to 150 degrees centigrade, and that is found that as the temperature increases, the impact energy in joules goes on reducing. Okay, and this is leads to the you can see associated with the conversion of this delta ferrite into the embittered phases like Z phase and 23/6 phase. Okay, then the micrograph of this specimens has been taken. So impact specimen aged at 300 for 5,000 hours for big pipe near notch. You can see notch here. In impact test, all of you are aware. So this is a notch. So nearby notch, this is a factor has been taken. There we dimples. See that there is a lot of dimples, but there are few cleavage faces also you are able to see in case of factographs. So this is a kind of a quasi cleavage, small cleavage and large fibrous structure you can see. But the same thing if you are tested away from that, so you can see a lot of dimples, means in the well itself there is something problem, the conversion is happening because of the maintenance of delta ferrite, but in base metal that is not the problem. So you can see small dimples. Okay, now you can see one more good picture where impact specimen aged at 400 degrees centigrade for 5,000 hour big pipe near the notch outer well tested at -S. So lot of inclusions. So when I was talking about the dimple fracture or a ductile failure, okay, so there are inclusion in a ductile matrix also leads to that kind of failure. That's what I was talking about. So here you can see after factography, one can say that there are inclusions and which plays a very important role for formation of cavities or formation of cracks. So because again it is a forming an interface, stress concentration is increasing, and because of the stress concentration, what is going to fail. But here also very interesting thing you can see, the dimples are very deep. Dimples are very deep, and size is little bit very small also. So these are the few observations one can make out, which you can predict what is happening in the material. So all these things are very important while developing a material, because failure is not only because of the bad design. Failure is most of the times because of the materials. That is what I would like to emphasize. So here is just an example for fatigue, factography related to fatigue failure you can see. So this is the cycle, and the typical mountain bike seat post has failed, and they are showed here the failure of the component. This is characterized by the beach marks. You can see these are the beach marks. Wherever they are concentrating, there is an initiation point. And if the same specimen, if you are taking under the scanning electron microscope, one can find the striations. So striations are nothing but these are the circular portions you can see, and one striation leads to one cycle of the fatigue failure. Okay, so these are the few things in factograph one can understand. So I will just summarize that material plays a very crucial role in failure of the component in practice. Proper understanding of the material behavior and macrostructural features is the key point to avoid such a failure in practice. By understanding this, design or processing of materials needs to be performed very carefully, and factography is helpful to recognize the cause of failure. So the flow behavior one has to understand very carefully, and then one can understand the macrostructural features. And once we have understood this, then definitely the selection of materials for the certain kinds of applications may be useful while at different environmental conditions. Okay, so with this, I hope I will end of this lecture. So thank you very much for listening patiently to all the audience. And again, I would like to thank to all organizers, organizing committee for inviting me to give a lecture. And I will be grateful to my professors under whom I have worked a lot, and with my parents and my last nothing but my wife. Well, thank you very much and have a nice day. Thank you very much.
Excuse me, sir.
Yes, sir. Yeah,
There
please.
are a few questions from the audience as well.
Yeah, sure.
Okay. So this one is from Ajay Kumar. He's
Yeah.
asking you, can you tell us some institutes in India which are open for material testing, certify and standardize product material if we start a startup, we as startup want to develop and deploy our product in the market?
Okay, so there are institute in a sense you want to say something like professional institute. Those who are testing metallurgical testings are available. So I please clarify that. Which one? Please, can you tell me once again what you want to say? Excuse me. Yeah, please clarify the question.
Yes, sir. Like, do you want me to
Yeah,
repeat the question?
yeah. Please.
Are this just a minute? Okay. So, can you tell us some institutes in India which are open for material testing, certify and standardize product material if we as startup want to develop and deploy our product in the market?
Yes, for material testing, there are a lot of labs available, which is under the NABL, okay, National Accreditation Board. So they have various metallurgical testings are available. As far as I am aware, in Mumbai, there are available. Even you can see they are open like IITs or NITs. They have a lot of material testing labs under FIST. Also, Government of India is funding for that. Okay, there are few labs definitely available for all kinds of material testing, from impact test, fatigue test, creep test. You can see or microstructural to see the metallography testing also. Yes, definitely, they are available. Yes.
I request everyone attending to please fill the feedback form as it will get closed by 3:20. Yes, sir. There is another question.
Yeah, please.
Are the standards, charts, and values given in our course book feasible in real material testing? How much percentage of
Uh,
deflection is there in theoretical and final product?
yes. A very nice question. Even I faced when I was working in Larsen and Toubro. There was a. I cannot share much, but I can tell you very interesting question. We have all design handbooks, and we used to have, and then still material is too fast. I'm just sharing with you within 1 or 2 minutes. What happened that one material has come to us, and that material is properly designed through the handbook and everything. Chemical composition is correct, but the impact properties are not meeting somehow. Because see, handbook has given based on some explanation previously done experiments, or over the period of time they have developed something. Definitely they are useful, no doubt. I am not denying the using of design handbooks for material purpose. Definitely that will be useful for purpose. But sometimes what happened that testing has been done on that, and at shop floor, or you can see at our level, we are doing some material processing. Then there could be a little bit of problem will happen. To increase the property, we are doing some testing or heat treatment, you can say. For example, it has happened like that. The material which has come to is a steel material, and it was not showing a proper impact. So that was the standard is giving as at minus 20 degrees centigrade, it should show 20 joule of impact resistance, but it was showing around 15 13 that way. But why it was happening? Then we have process again, go back to the from scratching. Material composition was correct, whether the heat treatment is correct or not, whatever has performed at the vendor level or not, that we try to find out. Then we have seen the microstructure of plan, and we have found that there are some ferrite stringents. Very interesting in failure analysis. So ferrite stringents, then we found there is some problem in the heat treatment itself. Because if you are heating the material above austenitizing temperature, you know all of you hardening how it can be done, and it is a quench into material, again heating for tempering purpose. So all austenite has to be converted into the martensite. Some written austenite has always been kept for the toughness thing, but still you can see the martensite has to be converted to tempered martensite. There should not be any ferrite is present inside that. And the ferrite is a BCC in nature. And BCC material, most of them showing the ductile to brittle transition temperature. Since ferrite was present inside that material, it is showing a very less value of impact resistance at low temperature. I told you around minus 20 degrees centigrade. And this ferrite leads to a failure. failure of the material, because this is showing the ductile to brittle transition temperature and the BCC in nature we don't want to have. Then how to avoid that problem? So then we have gone to the vendor side. We have seen how the heat treatment has been carried out for the big components. Then we found that once they are austenitized into the furnace for a certain period of time and temperature, as per this ASTM standards, they have around 25 millimeter for 1 hour, that kind of thing standard says. Okay, so but then they're taking from that and they're quenching into the well of oil. That's suddenly you big components, so they are quenching. So what is happening? They are putting into the oil, and again they are putting the you can see the face cover on that tank. Okay, and nothing was done. So what was happening, that whatever oil is coming into contact with the surface, they first get is hardening. But as the cooling progresses, the heat transfer rate get reduced. Heat transfer get reduced is a very fundamental thing. If heat transfer get reduced, so the heat cooling rate is going above the nose of the TTT diagram. If you see, very fundamental thing, then definitely instead of forming martensite, it is going to be formed either perlite or whatever that phase which is present in TTT according to that material. Okay, so that ferrite stitches is coming out because of that. So what was the solution in practice for that? So that we have given that time, either you rotate the component itself, it is not possible, then you rotate the oil, or we have to make sure that always the fresh oil is coming into the contact with the material. So these are the, you can see, practicing problem that is happening. And once they have done that part, again we have tested and it is showing the correct impact. And this is happening because ferrite stringents present inside that. And that's why I'm telling, understanding the material is very, very important. If you have knowledge about the ferrite, what is martensite, and this very fundamental we are learning in second year of engineering, mechanical engineering. So definitely that will be useful in that sense. It's a very fundamental thing, but industry, this kind of things is used to happen. And very interestingly, there are solutions for that also. Definitely you rely on the design handbook. They have took a lot of efforts to prepare that. But simultaneously you see these things also about the processing, and you see the chemical composition. If you have a feasibility to, before using the material, you test that material as per your requirement, and then you use, definitely that will be useful. That I can say. Okay, thank you.
Yes, so there are a couple of more questions, and then we can end the session.
Yeah, sure.
This is from NYC. In case of hyper velocity impact, what's a good material to go for?
Okay, at present, I may not be in a position to tell that way, but I can understand hyper velocity is a very, very large velocity that may be, so for what purpose, for what application he's talking about?
Unfortunately, is not mentioned itself.
Okay, yeah, but you can see in case of defense application, generally they are required to have high impact. So they are used to have the composite material for that. So composite has that advantage. We are not covered here since but composite, interesting thing, we have hard material, soft material, hard material, soft material. So those, the bullet is coming and pushing the soft material, okay, and it is hard material going further. So maybe I don't know exactly what he's talking about for pipe or whatever, but in defense they used to have this kind of composite materials, and nowadays they are using very. That's what I as far as to the best of my knowledge is concerned. Yeah.
And finally, there's another question where he's asking, how do you join ceramic and metal?
Yes, yeah, there are, you can see metal ceramics is the best way. You want to say joining, welding, you want to say, or you can make it a composite material. Instead of joining, one can make it up a composite material also for that. Ceramic and metal matrix composites are present. Like aluminum is having ceramic into that. Even magnesium is having silicon carbide. Ceramic is always been available. Okay, but as far as welding is concerned, if you want to join, either there are different ways of joining. You can have either go for welding or bolting. There are many methods you have learned in the engineering courses. Okay, but welding, we have to think of material, what kind of material that they are using, and then we have to go for welding, because ceramic is a very hard material. So it is having high temperature resistance also, but metal is not having that. So we have to take care of all these things that we have. Yeah, please.
Yes, sir. That was all the questions that they have posted.
Okay. So any other?
No, sir. Those are all the questions.
So, Dr. Kulkarni ji, very
Yeah.
presentation coupled with the case studies and recently published work. I know how painful it is polishing the material, and then that to magnesium alloy, and
Yes.
I know you're running around here and there. It's a difficult task, and that's the moment I think about materials. Your name, it's striking in my mind because the characterization, metallurgy, it's getting less attractive compared to other, the new fancy terms, new fancy populated
Yes.
area. But at the same time, we cannot ignore the metal characterization, and it's definitely very important. And very thanks for joining, accepting this, and then a very useful session. And I hope you have other your research is continuing, and we are following your publications. So
Yes. Yes. Sure. Sure.
please do that, and very thanks for your presentation. It's nice talk, and combined with your case studies and then recent publications. Very thanks, Kulkarni ji. Thanks.
Yes, thank you. Thank you very much to all of you for listening. I hope this may be useful for few of the audience also, and definitely for your career that may be useful. And with this, I'll also thank to all of you for patience listening. Have a nice day. Good day. Thank you.
Thanks.
Thank you.
Thank you, sir.
Good afternoon to everyone. After that informative session on fractography and role of materials in failure, I would like to introduce the next speaker for the session, who will be talking about the plastic deformation of high entropy alloys. Our speaker, before completing his postdoctoral research from TU Dresden, one of the best institutes in Germany, completed his BE majoring in mechanical from Anna University, Chennai. Further, he completed his ME in engineering design from the Government College of Engineering, Anna University, Chennai. Finally, finishing his PhD thesis on high entropy alloys from IIT Hyderabad. Before joining as a postdoctoral researcher, he was an experienced assistant professor and also was a senior research fellow before that. Over the years, he has published numerous research papers with good citation and has expressed his research interest in medium to high entropy alloys, micro or nano machining of high entropy alloys, and manufacturability of high entropy alloys. To take over this session, please welcome Dr. Dan Satyaraj.
Hello, hello, hello. Are you able to hear me, sir? Can you just tell me? Okay, yeah, fine. Yeah, fine. Okay, so good evening, everyone. So thank you for your introduction and also thank you for your invitation. So maybe I will share my slides. Seems to be my Wi-Fi is a little bit slow. Maybe possibly I will stop my video, then it will be audible. I feel like okay. So just I will close my camera, then I will start this session. Okay. So today, so I'm going to present about one of the future material for product development. So mainly I'm going to talk about high entropy alloys. So in that, so mainly I would like to focus on deformation behavior of these alloys. Okay, so I'm myself Dan Satyaraj, so faculty of mechanical engineering from IIT Indore. Okay, so this is the content I am going to cover today. So basically, I will introduce you into the concept of high entropy alloys, then what is the need of plastic deformation and what is the need of severe plastic deformation techniques. So those things I will cover today's session. Then mainly I will talk about what is the microstructure and texture evolution during deformation process. Okay. So finally, I would like to show some case studies on this advanced alloys called high entropy alloys. So mainly I will focus on FCC based alloys. So some of the basic deformation process, some of the severe plastic deformation and surface modification techniques. So those are the things I will cover today. So finally, I will conclude. Okay. So if you see, if you look into the history, so our human civilization is mainly based on the material development. So we had a Stone Age, so where we use the stone as a kind of so we use for our purpose. So then we had Bronze Age, then we had Iron Age. So during the Iron Age, so when we went to the Iron Age, so we started to investigate many composition, right? So many composition of steels to enhance the property of the material. So far, if you look into the periodic table, so far we identified almost around 118 elements in the present day. So we have been utilizing for our usage, right? So still, if you look into the periodic table, still we are need of new material, right? So for example, I can say high temperature application. So if I want to retain in the high temperature application for longer time, so still we are in the need of new material, right? So the material discovery always it's very important for the development. So in that point of view, I have been working in this new fascinating alloy for last 8 years. So whatever the work a little bit I did, so during my PhD and during my postdoctoral research, so I would like to present. Okay, so before that, just I would like to give the introduction about high entropy alloys. So most of the people don't know what is high entropy. So basically, just I will introduce you into the concept first, then I will go to the what is plastic deformation, then I will talk about case study. Okay, so first, if you see high entropy alloy, so it is nothing but, so this concept is first proposed by Professor A et al. In the year 2004. Basically, this term is, the term high entropy is coined by him. That's why it is called it like high entropy. Before that, the people already investigated the same alloy in the name of multi-component alloys. Okay, the name, the high entropy, it's come from its, mainly it is come from its configurational entropy of the system. If you see this equation here, here you can see the Gibbs-free equation. Suppose, so if you are adding many elements in the system, that will lead to the kind of very increase in the high configurational entropy, so which in turn decrease the free energy of the system. So if we decrease the free energy, basically I can get the very stable solid solution in the microstructure. So based on that, he tried to explain this high entropy concept. So based on the high entropy value, so we can divide the alloy into different categories. Suppose if it is greater than 1.5 R, it is called it like high entropy alloys. If it is in between 1 to 1.5, then it is called it like medium entropy. If it is below R, then it is called it like low entropy. Still, maybe you may not getting what I'm saying like a high entropy. Maybe I can I can explain about the definition of what is the high entropy alloy. So basically, the definition of high entropy alloy is nothing but usually this alloy has 5 principal elements, or ecoatomic or near ecoatomic proportion in the matrix. Okay, suppose for example, if you take the steel, so in the steel only the iron is the principal element, so the various elements are added into the steel to in order to align into the steel to enhance the property. But in the case of high entropy, so mostly all of these 5 elements will act as a principal element. Suppose I will check it in, if it is 100%, I will check it in each element in 20%, like that. So suppose if it is between 5 to 20%, then it is called it like high entropy alloys. Okay. So basically, this alloy has this 4 core effects. So already I told about what is high entropy effect. So this is mainly come from its configurational entropy of the system. Then it will stabilize the solid solution. So because of the solid solution, you may get the very good solution hardening. Okay. So that is the first core effect what they are discussing. Okay, so the second one is lattice distortion. So lattice distortion is nothing but, so suppose if I have the multi elements in the matrix, so if it is surrounded by different kind of atoms, so your system may suffer a very severe lattice strain. So this lattice strain can introduce the kind of very good mechanical properties like hardness and strength. You can able to enhance. Okay. Also, not only mechanical property, it also affects the physical properties. So the third core effect is this is sluggish, the kinetics of very sluggish diffusion. So mainly the sluggish diffusion, it comes from its atomic here. If you take atomic diffusion, it is very more difficult through the if it is the solid solution has more number of alloys, then the diffusion is really very difficult. Okay, so because the vacancy concentration is really very limited in this alloy. For example, here in the figure I showed the 5 component system of cobalt, chromium, iron, manganese, nickel. This is FCC based high entropy alloy. This alloy, if you take the diffusion of different elements in this particular system, this FCC based high entropy system, it gives the very high normalized activation energy than the other conventional alloys. If you compare it with the other steels, so it is giving the very high normalized activation energy. It means it gives the slower diffusion. Okay. If it is a slower diffusion, so you can get a very good better microstructural control. So because of that, we can enhance the property of the system. Okay. So another main core effect is cocktail effect. So this term was coined by our BSc Professor Ranganathan. So basically, it is nothing but, so suppose if you are mixing many elements together, that may give the unpredictable result than the what is the effect of the constitutive element. Okay. So this may be based on the material composition, microstructure. So many factors are involved in this. Okay. So if I see the microstructure, if I see the properties, basically this alloy has very good it has the very good specific strength than the other conventional alloys. So if you look into the few system of high entropy alloys, it has very good property than steels, titanium alloys, and also it has very good fracture toughness than the other conventional alloys. And also mainly so they are proposing this alloy for the high temperature application. So maybe some of the people are asking for what is the feature alloy for the high temperature application in this aeronautical aerospace industry. So basically this could be the answer. Basically, there are many systems are studied for the high temperature application. It gives the very good stability over the very high temperatures, and also very good wear resistance. This alloy has also, it has very good corrosion. So not only the mechanical properties, this alloy has very good physical properties like very high magnetic properties. Also, some of the systems are already reported in the literature. So in that point of view, this alloy has very good potential for the future application. Also, if you see the coating application, so some of the hard coatings, we can do it over the soft material. For example, here they did the high entropy coating with the titanium alloy, so they improve the surface properties. So these are all the example for the application of this feature alloys. So now I'm coming to the plastic deformation. So basically, so I will start with why we need for the plastic, what will happen during the plastic deformation. Suppose if I do the very simple tensile test, so clearly you can see that until the yield point, so there will be a the stress is directly proportional to the strain, so you won't see any deformation, right? So until this will be a linear elastic. So after the yield point, so clearly you can see that in the diagram you can see that there is a change in the shape of the your tensile sample, because your sample will undergo a permanent deformation. So the permanent deformation is, call it like a plastic deformation here. So the basic mechanism, what it begins it is mainly it is based on the atomic movements. Okay. Suppose if you take any, you may think that the real crystals, the crystal may have the atoms are arranged in the very regular fashion. Okay, but if you take the realistic condition, so most of the materials, the atoms are not arranged in the perfect fashion. Okay, always that has the material has the imperfection, kind of dislocation, vacancies. So that might help during the deformation. Okay, so basically the dislocation movement will help for the plastic deformation. So mainly in FCC, if I take the FCC metals or FCC material, there will be two different deformation processes will happen, slip and tuning. So here in this diagram, I will try to explain what is slip and tuning. Suppose just you assume in the left side, so we have the kind of extra plane of atoms, okay, in the figure. So when we are applying the stress, so this plane of atoms will try to bond with the next one, right side one, and it will try to move in the right side. Okay, so finally I will get the one step outside, right? So one step outside, I'm getting the deformation. So similarly, it will happen for many cases. So basically, here I showed the simple edge dislocation. There are many more dislocation process. It may happen the screw dislocation, climbing process. Also here I showed the what is the meaning of how the tuning will happen. So the tuning, how it will happen in the FCC means in case of FCC, each plane of atoms will move through a definite system, definite distance, and in the same direction. So in case of tuning, okay. So the extent of movement of each plane is basically proportional to its distance from the tuning plane. Basically your twin region will look like a mirror reflection to the each other. Suppose if I come for the left and right side, it will look like a mirror reflection of each other's. Okay, so now I am coming to the what is plastic deformation, like why what is the importance of plastic deformation. Suppose whatever may be the material, so we can made through mechanical alloying or by using the casting route, we may produce the material, but so in order to come to the application, so we have to make it into the certain shape, right? Suppose if I want to make a sheet out of it, I need to do some basic deformation process, right? So here the simple example I can say rolling. In the rolling process, so if I want to make some sheet out of it, I need to roll my material. Also, so in order to break down, suppose if your cast structure is having very high coarse grain, means you have to break down the coarse grain structure. So you have to do it by the hard forging. Okay. So these are all some of the basic deformation processes. So similarly, if I want to get some the rod out of it, then you have to do extrusion process. Suppose you want to get some cup shape, then you have to do some drawing process. So all the cases we have to do the plastic deformation. So now I'm coming to the what is severe plastic deformation. So severe plastic deformation is nothing but, so in case of severe plastic deformation, basically we can import the very high strain than the normal deformation. Okay, so like purposefully we are importing the heavy strain, so in order to modify the microstructure. Okay, suppose if you know the typical Hall pitch relationship, suppose if I reduce the grain size, so which in turn I can enhance the property of the material. So that is the case will happen in this severe plastic deformation. So by using this technique, we can generate the very high dislocation density, and also we can get the nanocrystalline structure at the final end. Okay. So with there are so many number of SPD processes. I'm going to today I'm going to say about certain important SPD processes. Suppose for example, here if I took here with respect to the axial symmetry, I can divide this process into high pressure torsion, twist extrusion. These are all some of the processes. And without axial symmetry, I can say equichannel angular extrusion and multi-axial forging. These are all some of the examples. And also with respect to the division of deformation shown, I can say some of the process, accumulative roll bonding and corrugation and straightening process. These are all some of the types of SPD processes. So we will see one by one certain few processes. Suppose if you take equichannel angular process, so in this case, basically the two channels, it will be the two intersecting channels. We will use it here. So basically, your sample will undergo a simple shear at this corner. Okay, so at this corner, your sample will undergo a very simple shear. Because of that, you can do the microstructure refinement, and also you can get the very high accumulation of strain in the samples. So usually in the case of SPD process, the sample size won't change before and after process. Okay, so only you will import the strain in the material. So these are all the some of the die designs you can see. Suppose for example, if I change this angle, basically I can change the what is the strain of my sample. So basically we can change this parameter and study the how the microstructural changes. So you can study by changing these angles, or by using these different processes. Okay, different routes. So basically here you can see in the route A, you can see without changing the shape, without changing the space. So we are doing the extrusion in the case of root gauge. So in the BC case, so basically they will flip the material and then they will try to do the ECAP process. So basically there are different routes are there. So based on the different routes also we can see how these processing parameters affect your microstructure and properties. So here, for example, here I showed the for the aluminum alloy. So after 4 pass, here you can see that very good nanostructured microstructure in the sample. Okay. So another process, this is accumulative roll bonding. So it is nothing but it is just a modification from the rolling process. So here we can do the you can join the two dissimilar metals by using this accumulative roll bonding process. Also, the similar material also can be rolled by using this ARB process. So basically, they will take the two different material and then they will roll 50%. They will roll inside the rolling machine. Then they will cut into the two again. Again they will stack it together. Again they will roll into 50%. So in this cycle they will do the ERP process. So by doing that, so we can enhance the high amount of strain, and also the number of layers will be increased at the end. Suppose for example, if I do 6 cycle, I will get the 64 layers with the finally I will get the nanostructure in the material. Okay. So another process, so this is some of the by using the high pressure torsion. So in this case only we can do the very small disc, but we can accumulate the more strain than the other process. Okay, because of the sample size is very small. Usually it is between 8 mm to the 10 mm. So they will place it over the anvil. In between the anvil, the lower anvil will be, through the lower anvil they will give the rotation, and through the upper anvil they will give the large amount of pressure over it. So because of that, it will undergo a shear and you will get a deformation in the structure. Okay, finally you will get very high accumulated strain in the samples. So basically this is the process will happen during this HPT process. So initially because of this more number of accumulation of dislocation will generate. Finally this dislocation will try to increase the misorientation and then try to align, and then finally it will form a sub grains. Okay. This process will happen in the HPT process. So multi-axial forging, again this is mainly used in the industry, so mainly to produce the this also ECAP process, but in this case all the sites will be forged at the final final step. It will be come to the same shape. Okay, again they will do the different phases will be forged in the different directions. So we can do the number of passes like this, same like a ECAP process. So this is another method. So in this case, so basically they will by using this V-shaped die, so they will try to bend the material, and then by using the flattened die, they will flatten your sample. So only we can do it for the flat samples in this repeated corrugation technique. Then finally you can impart the very high strain in the sample. So these are all some of the overall microstructure will get changed. So now I am going to introduce into the surface modification technique. So mainly these techniques are mainly used to produce the heterogeneous microstructure. Okay, so only suppose you want to enhance the property of the surface. So only in the surface you can modify your microstructure. So because of that you can improve the property of the surface. Okay. So in this case, maybe like here, because of this plunger, it looks like a friction stir welding, but here they won't weld the material. Only they will so over the surface they will do this. Just the plunger will go inside, and then they will rotate it. Because of that, so it will undergo a very high microstructural changes. Okay. So another technique, so these are all some other surface modification technique. Suppose if I take here, this is the surface mechanical adaptation treatment, SMAT process. Basically, it is called it like, just you assume like a small number of balls. It is kept in the like a piston die arrangement like that. You assume, okay. So one side of the top side, your samples are placed here. Suppose here the small many number of small balls are kept inside this plunger. So because of this vibration, this steel balls will get. So this will over this because of this high impact energy of these balls. So this surface will undergo a heavy deformation. Okay. So similarly here, this is the laser sharpening process. So in this process, they will use the very high laser. So that will fall on your sample surface. So that will induce a kind of very sharp wave. Okay. So because of this shock wave, that will induce the microstructure changes in the below the surface. So based on that, we can do the kind of surface modification process. Okay, for example, here I showed the certain examples of this laser sharpening. Suppose if I see here this connecting rod, so like you can precisely you can treat this material. So based on your application, suppose in this corner, if you want to enhance the property, so only in the particular zone we can do the laser pinning treatment. The tooling cost also really less, and also whatever maybe the complex geometry, you can do the laser sharpening process. So here you can see the impeller, how they are improving that this teeth properties, surface properties here. So now I'm coming to the what is the how it look like, what are all the information you will get from the microstructure, right? So basically, say if I look into this microstructure, I can say that what is my grain size, what is my grain size distribution. Also, if you see the microstructure, there is a color contrast in this map, right? So this color contrast, basically, I am thinking that it might be come from the orientation effect. Okay, basically this is the same phase. There is no secondary phase in this. So this color contrast, so mainly it is come from the grain orientation. Now I will introduce into the what is the grain orientation, what is the meaning of texture. Okay, so that is the thing we will see it in the further slides. Okay. Suppose if I see the texture, so the texture means nothing but it is weaver. So if I say the texture, you may think that the morphological texture, right? So you may think about the sari, it has surface texture. Also you may think about rocks also has the morphological texture. But what I'm talking here is the crystallographic texture. Okay, like crystallographic texture means suppose if I take any material, if I take metal, so mostly that will be polycrystalline in nature. So it means each metal has the very large million numbers of grains inside the material. So how these crystals or grains are oriented in the polycrystalline material. So that it tells about the what is your crystallographic texture. Okay. So suppose some possible arrangement of crystallites in the polycrystalline material. Here I showed here. Suppose if your material doesn't have any texture means, so all this crystal orientation will look like that. Okay. Suppose if it will be in the different direction. Suppose if it is arranged along x-axis, just you assume like that, then this grains will be arranged in the along the x-axis. So this normally these two cases are not at all possible in case of real real life situation. So mostly the grains will be have the certain grains have the similar orientation, but they are spatially apart. Okay, so if you see the material, so now we will see how to represent this texture, how to represent this different component of texture components. Okay, so mainly I'm going to focus on today. I'm going to focus on micro texture. So micro texture measurement through EBSD. Okay, like this is one of the characterization technique that is available in the scanning electron microscope. So based on that, I'm going to tell my all my results. So based on that, I will explain. Okay. So basically, there are different types of texture. Like macro texture, we can measure by the XRD diffraction. Meso texture that will relates with the misorientation and axis of boundaries. Okay. Suppose if I take any so why we have to go for texture means, suppose if I take certain application I want to emphasize here. Suppose if I take the electrical steels, okay, there if I could able to produce in certain orientation, so the orientation name is called gauss. If I generate this gauss orientation means, so basically I can reduce my core losses in the material. Okay, so also if I see the some of the aluminum cans, so maybe you know about this Coke cans. So there in the drawing process, so what's the problem here in this cans are, so that may induce the ears in the edge of the wall. You can see in the below diagram, you can see this earring problem. Suppose if I could able to generate certain cube orientation in the sample, I could able to get the desirable shape. Okay. Similarly, in order to get the very good high magnetic property, if I produce the cube texture, I can get the very good magnetic property in the sample. So finally, if I come to the mechanical property, suppose if I want to improve the tensile properties, suppose your texture is very less. Okay, if your texture is very random and also if it is isotropic, then you can get a very good mechanical properties or fatigue property in the samples. Okay. So now I will say like when these textures will develop. So basically, if you see from the starting from the crystallization and also during the plastic deformation, so when I do the heat treatment, so in all the processes, this texture will develop. Okay. So during also during this thin film growth, also these textures will the particular textures will develop. So most of the cases we have to control this texture or we have to modify the texture based on the deformation process or based on the heat treatment process. Okay, for example, here I for the texture here I showed this annealing texture. Basically, this sample has the very fine grains. Okay, like in the bottom side, you can see the very small number of many number of grains, but in the top side you can see only one grain. Okay, right? So what will happen is in this sample is, so due to the annealing, this certain orientation consume these small grains. So because of that, this particular orientation got strengthened in this particular sample. Okay, so this might be happen due to this precipitation or some other mobility advantage. There are so many mechanisms in this. So because of that, so it formed the particular texture component in the sample. Okay, so now I will try to explain how we can represent the texture. Like basically, there are so many ways to represent the texture based on the process. So mainly, so we will represent the texture based on the sample coordinate system and the crystal coordinate system. Okay, like sample coordinate system means nothing but, so it based on the geometry of the sample, so you will choose the coordinate system. Suppose if I take the rolling process, so along the rolling direction I will take I will set the one coordinate system, then transverse direction, then normal direction will be another coordinate system I will choose. So this specific coordinate system, how it is based on the crystal coordinate system, I will see. In the crystal coordinate system, so basically it has the 1 0 0 0 1 0 0 0 1. So like that I have to adapt in the during the coordinate system. Okay. So these are only some of the main mathematical parameters that is used to describe the orientation. So orientation, you can go with orientation matrix or Miller orientation, Euler angles. Based on that, you can describe your orientation. Okay, so these are basically based on ideal orientation, based on the Euler angles. The most of the research papers you can found. Okay, basically in the orientation matrix. So basically the position of the crystal orientation system with respect to the specimen coordinate system is defined. Okay, your orientation is defined in this fashion. So based on that, I can take this rotation or orientation matrix. So I will get this. So based on that, I will get this what is in my matrix. So based on that, I can say what is my crystallographic plane and what is my crystallographic direction. Finally, you can arrive. Okay. So another method is based on the pole figures. Okay, so pole figures means so based on these different poles, so you will try to show your different components. Okay, so here for example, here I showed the cube orientation. So in the 111 pole figure, this red colors will be the cube orientation. So this cube orientation will located in this direction. Okay, so in 101 pole figure, it will be look like that. Okay. So basically, this pole figure concept is mainly come from the stereographic projection. Okay, in this stereographic projection, so what they will try to represent this angular relationship between this planes and direction of different crystals in 2D. Okay. Suppose you assume that you have number of crystals in your sample. Just you are taking one crystal. Okay, one crystal. If you are placing inside the sphere, if I take the normal to that, so that normal will intersect with the certain poles, right? So certain poles in the sphere. So based on that particular plane, so here based on this particular plane, I can show my where is my pole. Okay, like if I take, there are three pole here will come because of these three planes. So I can show mainly this 111 pole here is represented for the FCC case. So they will represented by using this pole figure. Okay. Then another is the Euler angle. So how they will measure the Euler angle. Basically based on this, already I told about this, like in the orientation matrix, I told that concept, like how they will measure that crystallographic plane and direction. So similar like that. So here they will try to tell your crystallographic plane and direction as a point. Okay, so they will make it like a point in this space. Okay, in case of Euler angle. So just you assume like a cube. So inside the cube, there are so many points that will represent your they will cut the section. Okay, from the top, they will cut the section for at different angles. Then here they showed for the 5-degree angle, 5-degree interval. So with respect to 5-degree interval, here I can see the how my orientation will look inside my orientation distribution function. Okay, so this uh, 3D space and how it will look like in the pole figure. You can map is mainly for the suppose if your process is in only one direction, if it is, you can define your process in only one direction. Suppose for example, I can take your tensile deformation. Tensile deformation is only along the y direction, right? So in that case, you can mention by only by using the inverse pole figure map. Okay. So basically, these three different methods we will use for the represent the texture. So for example, pole figure. So we will take the distribution of crystallographic direction or plane with respect to the sample frame of reference. In the case of ODF, we will take distribution of orientation in terms of Euler angles. In case of inverse pole figure, we will take distribution of sample direction with respect to crystal frame of reference. Okay. So now I'm coming to the so today I'm going to talk about so mainly this microtexture. So the microtexture we can measure by using this EBSD technique. So EBSD is nothing but it is electron backscatter diffraction. This is one of the attachment they will attach in the SEM. So basically, by using this EBSD, you can get the lot amount of information from the same sample. For example, I can say about orientation mapping, about the grain size, about the texture measurement, and face identification, strain analysis. So all of the things we can do by EBSD. So the typical setup will be look like that. So you have to place your sample at a certain angle. Something it should be around 68 to 70 degree angle. You have to place the sample. Your EBSD detector will be here. So why we have to keep it in the certain angle means so this inclination will give some larger interaction volume. Because of this larger interaction volume, you will get a more more backscattered electron. So because of that, we can get the clear information about your crystal. So usually these diffracted patterns will form like a QQG bands. Because of the QQG band, you can able to index the what is your orientation in the sample. Okay, like this is the phenomena is happening in the EBSD. Suppose the escaping electron, if it is exit near the Bragg angle, so that will form a QQG band. So that is correspond to the each of the lattice diffracting crystal planes. So based on that, you will get a suppose if I have three QQG bands. So if I know the crystal phase, so I could able to index my particular orientation. Okay. Then by using the post-processing software, you can say what is your orientation mapping, what is your texture component is present in your material. All those things we can, after capturing this QQG pattern, so you can map by using the post-processing software. Okay. Suppose for example, here I showed this is your Euler map. Here they map the different texture components, right? So here the red color indicates the cube orientation of your sample. Cube orientation is nothing but it is 100 plane and 001 direction. So if it is Gauss is mentioned in the green color, then the crystallographic plane is 011 100 plane. So like that you can mention the different components in the, you can map the different components. Okay. So like you can see some deformation features also by using the EBSD. So for example, here I showed the for the austenitic sample during the cold rolling, they observed kind of deformation twins. So this deformation twins, it has certain orientation relations. Okay, like it has this misorientation exactly at the 60 degree. So based on this 60 degree misorientation, I can find out whether it is twin or not. Okay. Also, you can find out what is the fraction of annealing twins in your sample. So these also may be from austenitic steel. So during the annealing treatment, so that may induce the large number of sigma 3 boundaries. So that boundaries can be find out by using this technique. Okay. So also, what is the misorientation difference with the same component? You can see what is the misorientation difference. Also, you can study the here I showed the what are the different phases are present in the sample. So you can see, you can find out what is the different phases are present in your material, and also different kind of texture. So all the information you can get by your by using this technique. Okay. So now I'm coming to the case study. So mainly I'm going to tell about FCC based high entropy alloys. Okay. So in the case study, so in the first case study, so I would like to show simple cold rolling process, how it improve this property of this alloy. Then I will talk about little bit about different SPD processes. So same for the same alloy I will show. Okay, so mainly I worked in this copper, chromium, iron, manganese, nickel based high entropy alloy. So this is one of the metastable FCC. It has stable FCC phase. So basically, I took the material with this fine grain size. So initially, my texture is very random. If you see the pole figure, like my texture is really random. So when I'm starting the process, so after that, I try to roll it to the different reductions. Okay. So if I see here, if you see here. So in the 20%, it is nothing but it is a very little deformation. Basically, still you can distinguish the recrystallized grains. So after 60%, clearly you can see the significant change, right? So all the microstructure is started to align along the rolling direction, and also during this 90% deformation, clearly you can see the kind of shear bands, right? So it is something around 35 to 40 degree. So interestingly, if you see the texture, so initially it is random. So when I started to roll in the low reduction, it shows me a kind of copper type texture. Okay, this is mainly for that is for the pure metal type texture. So that kind of texture I could able to see in the pole figure. Like after heavy reduction, so basically I got the brass type texture. Brass type texture means this is alloy type texture. So by using that, so I could say that this alloy has very low stacking fault energy of this material can be related with this texture evolution. Okay. So this is some of the, I did bulk texture measurement. Bulk texture measurement also showed the very similar texture evolution. Clearly you can see that the brass and S component is enhanced after the heavy deformation, right? So even though the texture is really less, like here it is 3.2, it means the texture of this, even after heavy deformation, the texture of this material is really low. Okay. So also some of the researchers, they found deformation tuning during the deformation. This is basically from the some of the tensile tuning. So during the tensile process for the coarse grain size, so clearly they could be able to see the deformation tuning in the sample. Okay, in the fine grain size, there will be no tuning. Like with increasing the grain size, so there is a change in the mechanism. They found it is dominated by the deformation tuning. Okay. So after heavy deformation, so basically I got something around 200 nanometer grain size. So then I tried to anneal the material. So in order to enhance the ductility, so I tried to do the heat treatment. I produced the different recrystallized grains. So interestingly, this alloy until 900 degrees Celsius, there is no change in the microstructure. Right? It is very little coarse than the compared with the 650 degrees Celsius. So during the 700, I observed the fully recrystallization with the 1 micrometer grain size, and in 900 it is something around 2 micrometer. So only after 1000 degrees Celsius, so we observe the little coarser in the structure, like it is something around 20 micrometer grain size. But if you see the texture, there is basically there is no change in the texture. Okay, so basically it is getting weakened after the annealing process. So here in the misorient graph, here you can see the how the twins are increasing with respect to the annealing treatment. For the higher annealing temperature, the annealing twins are enhanced in this alloy. Also, if you look into the mechanical properties, so my ultra fine grain size is giving very good high hardness, high strength with appreciable ductility. So when suppose if grain sizes are increasing, then my ductility is enhanced with the expense of strength. Okay, so basically we understood. So what we understood from this rolling and heat treatment process. So in this alloy we could able to produce the ultra fine grain size, and then it has very good resistance against grain growth, and also the texture is really weak in this alloy. Okay, so mostly the texture, the recrystallized texture components are mainly it is related to the twin related components. So now I will try to show some of the like how we compare it with the other alloys. So here I showed like in this study I want to show just we compare this multi-component with the binary alloy. Okay, like nickel 60 cobalt. So why I compare it here means, so both alloy has the very similar stacking fault, and also I can see the what is the effect of multi-component, right? So multi-component of this HEA, so that I can differentiate. So in that sense, I try to do the both samples. I try to generate the similar grain size, and then I try to compare the texture of these two materials. Suppose this is the process I used to get the similar grain size. So like before starting the cold rolling, the both are same grain size. Then after rolling, so both develop the brass type texture. Okay, the very similar texture, very similar microstructure after cold rolling. Then I try to anneal at different temperatures in order to get the same grain size. Okay, suppose for example in HEA. Basically, I use the high temperature in order to get the similar grain size, because already I told this HEA has the very less grain growth, and also very resistance to grain growth. So because of that, I use the high temperature to obtain the similar grain size. So now if we see the microstructure of both cases, fine grain size to coarse grain size, so in the top side, so in the nickel cobalt, clearly you can see the difference in the texture, right? Like so in the orange color, it is dominating in the case of nickel 60 cobalt, but in the case of HEA, there is no change in the texture. So almost this texture component is homogeneous in case of HEA, but in the case of nickel 60 cobalt, the particular growth of this certain components like preferential growth of Gauss and G/P components, we could able to see in the microstructure. So here I plotted the different this grain size distribution of this different grain sizes. Clearly you can see that this nickel 60 cobalt have the very large number of grains, right? Like 400, 500 micrometer, you can see the grain size. But in the case of HEA, so almost it is there is no coarser grain size in case of HEA. Okay, so here I plotted the individual grain size, individual texture components. Here you can see how this texture component is evolved in the nickel 60 cobalt. So mainly it is due to the pinning effect. So pinning effect means nothing but, suppose for example, like during the deformation, this G and G/B might be very small in the not present in the material. Okay, so during the annealing, so that might be get the flavor during the grain growth. Okay, like earlier I showed the annealing texture, how these grains are consumed by the certain orientation. So same case happened in this nickel 60 cobalt, but in the case of high entropy, it does not happen, because this sluggish diffusion, it appears to be override this preferential grain boundary migration that leads to the very little change in the texture component. So that's why I'm getting the very homogeneous grain growth and homogeneous texture in this HEA. Okay, so this is the key observation from this study. You can see also now I try to compare it with the other medium entropy alloys. So I try to compare it with the other alloys. So with comparison with the 4 component, I didn't see any difference. Okay, in the case of 4 and 5, almost it's behaving very similar. But this 3 component, it is cobalt, iron, nickel. So usually it is showing the different texture during the annealing process. Okay, so during the annealing, so this alloy have some cube orientation. The cube orientation is dominated in case of medium entropy alloy. So that is a case happened with respect to the alloying addition. So now I will try to show some SPD process. Okay, this is some of the study did by Hamid, Professor Langdon group. They try to do the ECAP process. Already you may remember that process. Right, to two eq channels, they will try to pass the material. So they could able to do some four passes in the sample. Okay, like because of this four passes, so they could able to reduce the grain size around 100 nanometer. Okay, like by cold rolling, I could able to do 200. By using this ECAP process, they could able to do until 100 nanometers. So clearly you can see that in the Braidfeld image, there is like very nanostructure formation. So of these alloys, you can able to understand by this TM image. Also, if I see with respect to the process, so the significant enhancement in the yield strength of the material, yield and ultimate strength of the material. Here they plotted the what is the yield strength, what is ultimate strength with respect to the different passes. Also, if you compare the dislocation density, so with respect to the different like higher number of passes, it induced the very high dislocation density. Clearly you can see here in the range of 10 to the power of 9, you can see here. So also like Professor Stokesy work, so I would like to present here. So he is my postdoctoral supervisor. So they did some HPT process of this similar alloy. So what they try to do is, so basically they did the number of turns in the HPT process. So they try to reduce this ascast material of this cobalt, chromium, iron, manganese, nickel based alloy. So finally, they could be able to get the nanostructure in the case of this alloy. So basically, they got around 50 nanometer grain size after this HPT process. Okay, so by using this linear profile method, we can get the what's the grain size. Also, they did the TEM also. So basically, this is the grain size. What is the grain size they got for with respect to the different rotation? For the 5 rotation, basically it is come down to 25 nanometer. After 5 rotation, it come down to 25 nanometer in this alloy. So here clearly you can see the TM image of this HPT processed material. Also, the dislocation density is much higher in this case. So basically, during the HPT process, they got it around 10 power 14. Okay, like during the ECAP process, I showed 10 power 9. So in this case, very high dislocation density in the range of around 10 power 14. Okay, so also they try to study the texture evolution of this alloy. So if you see the texture evolution, it is giving the shear type texture. Okay, like this. These are also some another way how to represent this HPT processed material. So 0 to 180 degree they mentioned in the ODF session. So here you can see this B component, B bar, all this A star, all these components are shear related to the component. Okay, so this shear related component is formed during the HPT process. Although this texture is not that much sharp again. So already I told during the cold rolling the texture strength is something around 3.2. Here it is something around 4. It is not much compared to the conventional alloys. Okay. So this is the hardness value. How they could able to go until 500. They got it after the 5 rotation. So from this study we could able to understand. So we got the they got very steady state crystalline size in the range of 25 nanometer, very high dislocation density, and also weak brass texture, shear texture. Okay. So now I would like to show the what will happen during the tensile deformation of this alloy. So I took something around 20 micrometer grain size. I tried to do at different temperatures. Okay, so I did until helium temperature. Okay, so already I told in the tensile process. So usually we have to mention in terms of IPF map we can represent the texture, right? So during the room temperature, I didn't see much twin, right? So in the red color lines here, it is indicating the twins. So I could be able to see very less number of deformation twins during the room temperature deformation. But at the same case, if I go to the cryogenic temperature or helium temperature, you can see large number of deformation twins. So this red color lines, it's indicating the deformation twins. So large number of twins should be able to see it in the low temperature. So that affect the your texture of the material. Like for in this case, so it is forming 111 and mixture of 111 and 0011 001 fiber texture is forming in this tensile deformation. Okay. So also some people they try to do the cold drawn of this same alloy. So you can see the with respect to the drawn direction, this microstructure is aligned, right? So these bands, like it is along the drawn direction, this microstructure is started to align, and finally they also got the 111 and 100 fiber after the cold drawn. So similar to the tensile. So similarly, I can show the deep drawing process also in the same material. So in the deep drawing process also, they got very good drawing ratio, something around 2. They got it for this 5-component system. Also here also the texture is forming, alpha fiber is forming. Also during this deformation process, they got the deformation twinning at the edge of this cup. So basically in the edge of this cup they observe the deformation twin. So here you can see in various places how the microstructure. So basically here the green color indicates the dislocation. Okay, like large number of dislocations are formed during the drawing process. Okay, so now I would like to show what is the work what I'm doing here in the IIT Indore. So I'm trying to do some surface modification technique of this same alloy. So why we have to go for laser sharpening means, so already I told, so this is some of the surface modification technique. So if you change the surface modification technique, if you change the surface, so basically you can improve the fatigue strength of the material, right? So the fatigue strength has the positive relationship with the tensile strength. So all we know it. So if I change the surface, so basically I could enhance the fatigue strength of this material. So already in that direction, the few people are working in this direction. So basically they try to reduce the grain size, and then they studied the fatigue strength of this material. So basically this fine grain size have very good fatigue ratio, something around 0.32. So already they observed in this material. So in that point of view, I try to do the I tried to produce the ultra fine grain size, plus I want to do the laser sharpening over the sample. Okay, so already I told about the process. So what will happen during the laser sharpening? Because of this very shock wave, this high energy plasma that will induce a shock wave inside the material. So this will generate a kind of compressive residual strength. So this compressive residual strength is really beneficial for your fatigue life of the material. Okay. So basically this is the LSP process. So how it will happen? Basically the high energy plasma that is converted to the shock wave that will create a compressive residual strength. So this is the setup we have in our lab. I did with Professor Palani. So basically we use the NDIAC laser, continuous laser to generate this laser pulse. So this is the like we can control the stage. So basically here we can control the XY stage, XY movement of the sample. So along the one direction, I try to do along the Y direction. I try to do this shock pinning. Then what is the changes in the microstructure, I will try to show in the next few slides. Then I will conclude my talk. So basically my initial grain size is something around 20 micrometer, and then I cold roll to very heavily cold roll this material, and then anneal at different temperatures, so in order to produce the ultra fine grain size, right? So already I told my objective is to generate ultra fine grain size, and then I have to do the surface modification. So I generated this 550 nanometer in this same alloy. So this at this particular temperature, it is forming the sigma phase also. So basically at 650, so I could able to form the sigma phase in this material. That also beneficial for strength of this material. Okay. So because of this nano precipitate, I could able to enhance the strength. So one case I annealed at 800, so that is around 1 micrometer. It doesn't have any precipitate. Okay. So these both conditions. In this both condition, I tried to do the laser sharpening. So after sharpening, I could be able to reduce near the surface, like at least this sharpening, it is affected around 100 micrometer below the surface. So below the surface, I just measure this microstructure. It is something around 345 nanometer. I got it below the surface, and also high dislocation density also formed by, we can understand from the this low angle boundaries. Also this 800-degree sample condition also it induced the very good reduction in the grain size. It is something around 500 nanometer. It also formed the very good high dislocation density. And also I measured some residual strength in this material. It is forming the compressive residual strength. In both cases, also I tried to see the surface roughness of the material. So why I had to see the surface roughness means here whether this laser plasma, whether it is affected the surface, how much affected the surface, that I want to see it. So in that purpose, I did it in the two environments. So this laser sharpening I did with the water environment and without water environment, but with water environment it is showing the very good surface roughness properties. If you see here, so this is without medium, how rough your surface, but like inside the water it is very less affected. And also I tried to do the micro harness along different thickness. So below the surface there is a significant enhancement in the hardness value, but inside the microstructure is almost very similar. And also I tried to do some tensile tests. Clearly we could see the improvement in the property. Still I have to do the fatigue test. Maybe I will update in the next lecture maybe. So based on this study, we can be able to understand that laser sharpening, it is giving very good grain reduction, and also there is improvement in the hardness and tensile properties. We could able to see after laser sharpening. So hence this tensile property is positive relationship with the fatigue life. I hope fatigue life of the sample also might be improved because of this laser sharpening process. So with this, maybe I would like to conclude our today's session. So maybe you may get some information about what is plastic deformation, what is severe plastic deformation, and maybe for students it might be useful for how to represent the data, how to present the data, right? So finally, so I would like to emphasize microstructure, processing, and performance of material may be appreciated. So I am dreaming that this high entropy alloy could be the future material. So let's see. So with this, I will just wind up our today's session. So this is, so I would like to show what are the areas what I'm working here. So mainly I'm working in this plastic deformation and SPD processes and surface modification technique, and also I'm working in micro and nano machining of this high entropy alloys. Also, I'm planning to work in low temperature deformation of these alloys. So these are all my research areas. So finally, I would like to thank you all. Thank you all for your time. So now it's open for questions. Maybe I can I can clear some of your queries now. So let's see. Thank you all. Thank you for your time.
Yes, sir. Hello, sir.
Yeah,
Yeah, there are a few questions that have been posted.
yeah.
The first one is what is the effect of grain size and dislocations on corrosion rate of metals?
Corrosion grade of metals.
Yes, sir. Corrosion rate of metals.
Yeah, certainly it will affect, right? So if you enhance the dislocation, that is detrimental for the corrosion. So that is the way they will try to do this surface modification technique. So certainly you can improve it. Like, so what is the question? Can you just repeat it?
Yes, sir. So
What's the
what is
relation
the
between microstructure and dislocation?
no? What is the effect of grain size and dislocation on corrosion rate of metals?
So metals means I can't say like a common metal. So see, with respect to the each different metals, it will behave differently. But overall, if I take the grain size, so if I decrease the grain size, so basically I can improve the corrosion resistance, right? So that is the way. So we can do it. So even both, if I do the plastic deformation, dislocation density also will enhance, but that might be detrimental for some cases. It might be the detrimental for the corrosion. Okay. So that is my answer. So they have to wisely select the metal, like what kind of application they are looking for. So based on that, they need to select. Okay. Any other question?
What
Tanush?
are the difficulties in manufacturing titanium alloys for high-speed aircraft impeller blades?
No. What's the question? Can you just
Yes, sir. What are the difficulties in manufacturing titanium alloys for high-speed aircraft impeller blades?
impeller blades? So I don't know. I don't know idea about titanium alloys. So mainly in the titanium alloys, what is the problem is oxidation is the main problem. So when we are doing the manufacturing, the oxidation problem is the main problem in this titanium alloys. So that might be the reason. But with respect to the application, I don't know what is the difficulty. Okay, so the general thing, what's the difficulty in titanium is the oxidation problem is the main problem. Okay, so that is the thing I can say.
Okay, sir.
Yeah.
So there's one more where he's asking, what is your point of view on deformation of turbine blades of Kaveri engine and how to overcome it?
Deformation of turbine plates. Oh, what's the failure of Kaveri engine? So
Yes, sir.
basically that I don't know about that mechanism. Really, I never looked into the Kaveri engine. So what's the problem? So we have to see. So right now I don't know idea actually what happened to the Kaveri engine. Yeah.
So there's one more. Are there any alternatives for blade material for turbofan and turboprop shaft and
Yeah,
blade material?
that's what I proposed today. Like this is the one of the very good future material for the high temperature application. So in that point of view, there are so many systems of high entropy alloy. So if I look into if you see the literature, there are so many systems are people are already studying for this towards this high temperature application. So not only high entropy alloy. So basically nowadays they are trying to mix it with the carbides. They are making like high entropy carbides and mix it with the other composite. They try to say like high entropy composite. There are so many, based on this concept, there are so many different new alloys or researchers are proposed. So that might be the replacement for the turbines. Okay, so that is my answer for this question.
Okay, sir. So that was the last of questions, and thank you for your wonderful insight.
Yes, yeah.
I invite Professor Reynolds to move on with the session.
Okay.
Dear Professor, I am really happy for this wonderful session.
Yeah, thank you.
And I think the participants are rewarded for their time with all the informations that you have given. So
Yeah.
it is a lot of informations,
Yes,
and
sir.
students who are into other fields, they can take up this material research, because it is one of the very interesting field which
Yes,
is
sir.
not explored by our students.
Yeah.
Mostly they go into carbon fiber, composites, and other things. So this material characterization, all those things are really very interesting, no, which students can take up. And no, your session is really, it is really very good, and the energy that you give, it is really very high entropy session.
Yeah.
And and after seeing all your sessions, no, I can tell the severe plastic deformation that you have undergone, no, to do all this research and the presentation. I can see it. No, your lectures was really laser sharp, I can tell you. Okay, so it's really great, sir. So no, we will share your interactions, no, and we like to invite you again and again for all these type of wonderful interactions. And my co-convener, my fellow Sir Srinivasan Narayanan, is really no wanted to thank you. So once
Yes,
again,
sir.
Okay, thank you,
Yes,
sir.
sir.
Thank you very much.
I'm very happy. It's like a complete package from the beginning,
Yeah.
introduction to SPD, and I'm kind of, I think you know, but I'm also a bit into this EBSD. I'm
Yes, sir.
actually love to see EBSD
Okay,
and image
thanks, sir.
quality map. It's very great, fantastic. And I have one question.
Yes. Yes, sir.
How difficult or how easy it is high entropy alloy material polishing for EBSD?
So it is based on the phase, like what is the kind of different phases are present in your sample. So based on that, it might be difficult. Like suppose if it is
Generally,
generally single phase means it's very easy. Single phase, or if it is dual phase, it's very easy to do it. Like by using this standard perchloric acid and so this methanol. So by using this proportion, we can play around this proportion. So we can do the electropolishing. So certainly we can do it. But if it is there is some intermetallics. So even nowadays people are proposing this intermetallic high entropy alloys. So that also giving very good property. So in that case the etching is the problem. Like intermetallic case, the polishing, and maybe we have to go for pips or something other methods. So we can do it. So it's not a problem. First we have to do the XRD, then we have to find out the phase. Based on that, we have to generate the cry file in the EBSD. Then by using that cry file, again we can index what are the phases in the samples. So,
the very basic reason for this is
yeah,
I'm more of custom stainless steel and magnesium alloy. I have a two great, two different. Magnesium is
yeah,
custom stainless is different.
yeah,
So I have a lot of experience. I mean, to certain extent. This entropy alloy, this preparation, I'm wondering, and all great microstructure. It's like we are also doctor. Wherever there is a problem, we just go and address laser pinning, laser based treatment. So
okay, okay,
helpful for sensitization, where I have published a lot of material on this in the area of sensitization. So I'm
okay.
to series. So wherever there is a sensitized microstructure, I want your facility to go on directly.
Definitely, definitely.
So it's
Yeah. You can always. It is open for collaboration. So we are
yes.
so in MSME we have the EBSD facility. So we can do it. No problem.
Yes, sir. Thanks for presentation. As
Yes, sir.
Professor Renal pointed out, it's higher, energy presentation, and nothing, it's nothing has come to its constant same flow. I mean, and, fantastic, sir. Thanks for the energy.
Thank you, sir. Thank you, sir. Thank you very much. Yeah.
Thank you, Professor. Thanks a lot.
Yeah, thank you.
So, dear participants, so we'll be joining for the next session by 5 p.m. and the next session will be handled by Engineer Joseph Rajkumar from Adient, USA. So his session is product design and development for automotive systems. So we'll be joining by 5. Thank you, Professor.